All right, let's get right into it. For something like 40 years, there's been this simple story told in theoretical computer science, a story about a proof system called resolution. But what if I told you that story, the one repeated in countless textbooks and lectures, is basically a myth? In this explainer, we're going to pull back the curtain and see what the research really says compared to what everyone thinks it says.
If you've ever taken a class on computational complexity, this probably sounds super familiar, right? The gospel is, resolution is weak. Some guy named Hawken proved it way back in '85 with the pigeonhole principle. And because of that, we need to find stronger proof systems. This is treated as settled fact. But it's missing some details, some huge, game-changing details that flip the whole story on its head.
So here's the real punchline. That common claim, it's a massive oversimplification. The actual research proves something way more specific. It's not that resolution as a whole is weak. No, it's that certain, very particular restricted versions of it are weak, and only when you throw these specially engineered, almost artificial problems at them. And that distinction? Well, that's everything.
Okay, so to really get to the bottom of this, we have to go back in time. Right back to this source, the paper that kicked this all off. Armin Hacken's foundational 1985 work, The Intractability of Resolution. This is ground zero for the whole resolution is weak story. And boom, right there inside the paper itself is the first clue everyone seems to just gloss over. Hacken explicitly says he's modeling his proofs as binary trees. Now, you might think that's just some minor technical point, but no way. It is the absolute bedrock of his entire argument. He wasn't looking at the kind of general resolution we use today. He was only analyzing what's called tree-like resolution.
And this slide really shows you why that matters so much. On the left, you've got the tree-like structure from Hawken's paper. Think of it like this. If you figure something out, a new clause, you can only use it once on any single line of reasoning. But then look at the right. That's how modern SAT solvers actually think. They use a structure called a directed acyclic graph, or a DAG. And this lets them do something amazing: clause learning. They can discover a new fact and then reuse it over and over and over again. It's way more powerful, and Hawken's proof simply doesn't apply to it.
So you might be thinking, okay, Hawken's paper was specific, but surely later research made it more general, right? And the answer is, sort of. The story definitely continues after Hawken, but as we follow the clues, we start to see this really interesting pattern emerge. With each new proof, the problems being studied get even more restricted.
This timeline just lays it all out. 1985, Hawken's proof is stuck with tree-like systems. Then, fast forward to 2001. Ben-Sasson and Wiggerson finally crack a proof for the more general DAG resolution, which is awesome. But, and this is a huge but, it only works for pigeonhole principal problems that are encoded onto this very specific mathematical object called an expander graph. A couple years later, Razborov does something similar, but again, only for problems on dense, unbalanced graphs. Do you see the trend here? As the proof systems in the theory get more powerful, the problems they can prove things about get more and more exotic.
And all of this brings us to what is maybe the single most important concept to get your head around this whole fallacy. We have to draw a really sharp line in the sand between two very different kinds of problems. What we can call the vanilla pigeonhole principle and the structured pigeonhole principle. They are not the same beast at all.
Let's just walk through this. Vanilla PHP is the one you learned in school. N+1 pigeons and holes. Any pigeon can try to go into any hole. It's simple, it's clean. And here's the big secret. Proving that this version is exponentially hard for modern DAG-like resolution is still an open problem. That's right, nobody's actually done it. The structured versions, on the other hand, are what those famous papers used. They add this whole extra layer, a graph, that restricts which pigeons can even go to which holes. And it turns out, the hardness in those proofs comes from the crazy combinatorial structure of the graph itself, not really from the simple pigeon principle anymore.
So why do we even care? Is this just a bunch of academics splitting hairs? No, absolutely not. This 40-year-old misunderstanding has had real, actual consequences on the field of computer science. It really matters.
I mean, for one thing, it sends researchers down the wrong path, trying to invent stronger systems when we haven't even fully understood the power of the one we've got. It totally distorts how we teach students, giving them this incomplete picture. But the biggest one for me is that it creates this bizarre world where theorists are all saying resolution is weak, while at the exact same time, practitioners are using SAT solvers, powered by resolution, to solve gigantic, real-world industrial problems with millions of variables. It just doesn't add up.
So let's just correct the record. Resolution is not weak. period. It is an incredibly powerful and stunningly efficient system for the vast majority of messy, asymmetric problems that we actually face in the real world. Its supposed weakness only ever shows up when we cook up these very specific, highly symmetric, combinatorial problems, like those graph-based ones.
Okay, so let's boil it all down. Here are the 4 things to remember. 1. Haken's famous result is only for tree-like resolution. 2. All those later proofs for modern DAG resolution, they only work for those superstructured artificial problems. 3. And this is the big one, whether the plain old vanilla pigeonhole principle is actually hard for modern resolution is still an open question. And 4. The power of resolution isn't black and white, it's nuanced. It all depends on the problem you give it.
And that leaves us with this huge, tantalizing question mark hanging over the entire field. Could it be that the simplest, most intuitive version of the pigeonhole principle is actually easy for our modern tools? We still don't have the answer. So the next time you hear someone casually say, resolution is weak, you'll know the real story. You'll know that in theoretical computer science, the details aren't just details, they're everything.